In the dark between stars, nature builds worlds that seem to ignore our instincts about what a planet should be. Across hundreds of light years, faint dimmings, subtle wobbles, and slivers of starlight filtered through alien skies reveal objects so unfamiliar that even their categories begin to blur. These are not destinations. They are experiments formed by gravity, time, and radiation, each one a clue to how far planetary diversity can stretch before our definitions break. One of the strangest silhouettes ever recorded did not announce itself with a crisp planetary shadow. Instead, it arrived as a complex, lingering eclipse, an intricate pattern of dips that suggested something vast, structured, and in motion. The object behind that signal is known as J1407b, located roughly 434 light years from Earth. Astronomers have wrestled with its true nature, in part because its mass is difficult to pin down. Estimates place it somewhere around 10 to 40 times the mass of Jupiter. At those scales, it sits near the boundary where planet and brown dwarf become a matter of formation history as much as weight. Yet the defining feature is not its uncertain mass, it is the architecture surrounding it. Evidence points to a ring system so large that it dwarfs anything in our solar system. Around 30 distinct rings, spanning an estimated total diameter of about 120 million kilometers. That scale is roughly 200 times the extent of Saturn's rings. If a similar structure encircled a planet near Earth, it would not be a detail in the sky. It would be a dominant celestial presence, bright and impossibly wide. Such rings are not merely decoration. They are a stage in evolution. Over time, ring material can clump, collide, and begin the long process of assembling moons. The very grandeur that makes a ring system spectacular can also mark it as temporary on astronomical timescales, destined to thin as satellites emerge and sweep lanes clean. In that sense, J1407b may be less a finished world than a snapshot of construction caught in the act. From there, the catalog of oddities deepens, not by breaking physics, but by exploring its extremes. Consider a young giant called GJ 504b, about 57 light years away. It carries roughly 4 Jupiter masses while remaining close to Jupiter in size, with a radius near 1.16 times Jupiter's. What makes it memorable is not a ring or a storm, but its color. Observations show it glowing with a subdued pinkish tone. The likely reason lies in youth. If the system is around 160 million years old, the planet still retains heat from its formation, radiating that energy away as it cools. That remnant warmth can tint the planet's emitted light toward a dull magenta, a thermal afterimage of its birth. Color, however, is only one way a world can be unlike Earth. Some differences are buried under pressure. GJ1214b, often described as a Neptune-like water-rich planet, has a mass a bit over 8 Earth masses and a radius about 0.245 times Jupiter's. Its appeal, at first glance, is the suggestion of abundant water. But water does not guarantee oceans, beaches, or anything that resembles a shoreline. The planet is not thought to offer a solid surface in the familiar sense, and its atmosphere and interior conditions are far removed from terrestrial comfort. At temperatures reaching around 280 degrees Celsius and under enormous pressure, water would not behave as it does in Earth's seas or clouds. Instead of cycling neatly between ice, liquid, and vapor, it can exist as a supercritical fluid, an exotic state that is neither purely liquid nor gas, yet shares properties of both. In that regime, weather and ocean become misleading words. Chemistry changes, density gradients shift, even the way heat moves through the atmosphere is altered. A planet can be rich in water and still be profoundly inhospitable to the structures life uses on Earth. Then there are worlds sculpted by stellar death, where a planet becomes a survivor rather than a child. In the constellation Cygnus, about 650 light years away, lies Kepler 70b, an object with a mass around 0.44 Earths and a radius about 0.75 Earths. It is tiny by exoplanet standards and violently hot. The star it orbits is no longer a normal, steady main sequence sun. It once was. But it passed through a red giant phase, swelling outward and transforming the architecture of its system. Kepler 70b is thought to be the remnant of something far larger, a former gas giant stripped down to a dense core after enduring the expansion of its star. The planet now circles at about 0.006 astronomical units, roughly 65 times closer to its star than Mercury is to the Sun. Under that relentless irradiation, the estimated temperature climbs to about 6,650 degrees Celsius, hotter than the surface of our own Sun at roughly 5,500 degrees. At such temperatures, rock is not rock in the ordinary sense. Matter softens into new behavior, and the planet itself may be slowly evaporating, losing mass into space like a fading ember. Extreme heat appears again in another system, but with a different kind of consequence. WASP-76b, roughly 640 light years away, is a gas giant with about 0.92 times Jupiter's mass and an inflated radius near 1.83 Jupiter radii. It orbits so close to its star that it is tidally locked, keeping the same face turned toward the light at all times. The day side is heated to around 2,350 degrees Celsius, hot enough to vaporize metals. Under that furnace sky, iron can enter the atmosphere as gas, but the planet's far side never sees the star. There, temperatures drop to nearly half the day side's intensity. That contrast powers fierce winds that transport vaporized iron from the hot hemisphere to the cooler one. As the gas migrates into lower temperatures, it condenses and falls, an alien precipitation of molten metal. The process is an atmosphere behaving like a planetary scale foundry, where the familiar concept of rain survives. But the substance has changed into something that would annihilate any ordinary surface it touched. Not all extremes come from sunlight. Some come from the compact ruins of stars. PSRJ 1719-1438b orbits a neutron star only about 20 kilometers across, a remnant so dense that a teaspoon of its matter would weigh billions of tons on Earth. This neutron star is also a millisecond pulsar, spinning once every 5.4 milliseconds around 10,000 rotations per minute, sweeping beams of radiation through space like cosmic lighthouse arcs. Circling this object is a companion about 40% Jupiter's size, yet with a mass greater than Jupiter, around 1.2 Jupiter masses. Small radius, high mass, the combination implies extraordinary density. The prevailing explanation is that this planet is the stripped core of a former star, its outer layers removed by interaction with the pulsar. What remains is a carbon-rich remnant, often described as a diamond-like world, roughly 5 times Earth's size, with a diameter near 60,000 kilometers. The orbit is so tight that the entire system could fit inside the sun's diameter, compressing a drama of stellar evolution into a space smaller than the void between our own star and its nearest planets. Density can become strange even without neutron stars. WASP-107b is a gas giant that has forced astronomers to revisit assumptions about how planets acquire their envelopes. Its radius is close to Jupiter's, around 0.94 Jupiter radii, yet its mass is only about 30.5 Earth masses. By comparison, Jupiter is about 300 Earth masses. That means WASP 107b is puffy and low in density, more like a tenuous sphere of gas than a compact giant. Models suggest its core may be only about 4 times the mass of Earth's core, when some expectations would place it nearer 10. If the core is indeed that small, it raises questions about how such a planet gathered and retained so much atmosphere without building a correspondingly massive interior. In the quiet math of formation theory, objects like this are disruptive because they hint that there are multiple pathways to becoming a giant, some of them gentler, some faster, and some still not fully understood. Among the worlds discussed so far, the environments sound hostile by default, too hot, too dense, too irradiated, too strange in chemistry. Yet astronomy continues to search for planets that might offer a narrower bridge to habitability. Gliese 581d has been considered in that context because of its relative proximity within about 20 light years, and its mass roughly 6 times Earth's. It resides in the habitable zone of its star, the region where temperatures could allow liquid water under the right atmospheric conditions. But habitable zone is not a promise. If the planet is tidally locked, one hemisphere would face perpetual day while the other remains in enduring night. Such a configuration threatens the night side with deep freezing and the day side with constant heating. A thick atmosphere rich in carbon dioxide could soften that contrast by trapping heat and transporting it around the planet, potentially preventing the dark hemisphere from becoming a permanent ice trap. If any region offered the most stable conditions, it might be near the boundary between light and darkness, the twilight band, where temperatures could be less extreme than at either pole of day or night. Even distance itself can become an oddity. 2MASSJ2126 was once discussed as a lonely, free-floating object wandering between stars. Later work connected it to a star named TYC 9486-927-1, with both lying roughly 104 light-years from the Sun. The truly unusual feature is the separation. The planet appears to orbit at about 1 trillion kilometers, roughly 7,000 times the Earth-Sun distance. At such a remove, a year is not a season, but an epoch. Around 900,000 Earth years for a single orbit. An orbit that wide challenges intuition about gravitational binding in a galaxy full of passing stars and tidal disturbances. Systems like this force astronomers to ask how such companionship survives. Was the planet born in place and then scattered outward by encounters with other massive bodies? Was it captured? Or did it form more like a low-mass companion in a wide binary arrangement? Each possibility carries implications for the hidden dynamical histories of planetary systems. While planets draw attention, their moons may carry equally important stories, especially about formation. Detecting exomoons is notoriously difficult. They are small, faint, and their signals are easily tangled with noise and stellar variability. Yet there is now clear evidence not of a finished moon, but of the environment that makes moons. Around the young, massive exoplanet PDS 70c, observations using the ALMA array in Chile have revealed a disk of material encircling the planet, a moon-forming disk, or circumplanetary disk. The amount of material inferred in this disk is enough to build several satellites, potentially 3 bodies comparable in mass to Earth's moon. This matters because it turns a theoretical process into something we can watch indirectly in real time. A planet with its own subdisk nested inside the larger disk of a young star system. like a smaller whirlpool inside a larger current. It is planetary formation continuing at a second scale, building not a world, but a system. Some of the strangest gravitational choreography appears not in disks, but in multi star architecture. KOI 5AB is notable less for its own physical extremes than for the intricate family it inhabits. The planet, about half the size of Saturn, orbits Star A in a triple star system. Star A has a close companion, Star B, with the pair orbiting each other roughly every 30 years. A third star, C, is gravitationally bound as well, taking about 400 years to orbit the inner pair. A planet in such an environment must persist amid shifting gravitational tides. The changing pull can tilt or perturb orbits over time, complicating the quiet stability that single star systems take for granted. If one could hover above the planet's cloud tops, the sky would not be anchored by a single sun. Light would come from multiple sources with different brightness and apparent sizes, turning day into a dynamic geometry rather than a predictable arc. These discoveries carry a hidden lesson. Most of what we see of exoplanets is inference. A ring system becomes legible through the timing of starlight dips. Atmospheric metals reveal themselves through subtle imprints and spectra. A moon-forming disk appears as a pattern of millimeter emission. In nearly every case, the world itself is a point of light lost in the glare of a star, and yet its properties are extracted with remarkable precision. And still, the universe may be holding categories we have not confirmed. Some researchers have speculated about planets, hypothetical planets forming in the disks of gas and dust that can surround black holes. If such objects exist, they would evolve in environments shaped by extreme gravity and energetic radiation, and their orbits could stretch across such enormous scales that a single revolution might take millions of years. They remain unobserved, but the idea underscores how planet formation could be less tied to familiar stellar nurseries than once assumed. From a ringed colossus like J1407b to a metal-raining giant like WASP 76b, from an ultra-hot remnant like Kepler 70b to a diamond-like survivor orbiting a pulsar, the pattern is not chaos. It is variation, physics repeating its rules under different initial conditions. Each planet is a boundary test, a way of learning which models hold and which require revision. The story of exoplanets is ultimately a story of humility. Our solar system taught early astronomers a neat progression of worlds, but the galaxy does not owe us simplicity. With more than 5,000 known exoplanets and counting, every new detection expands the parameter space of what planet can mean. The next strange world may not be bigger, hotter, or denser than the last. It may simply be different in a way no one predicted, waiting in the faintest dip of starlight on the edge of measurement where discovery begins.